Right now, without moving a muscle, you are traveling at the fastest speed anything in this universe is permitted to travel. Not through space, through time. Every atom in your body is being carried forward through the time direction at the maximum possible rate, and you have never once had the option to stop. Be careful with that, because if even a sliver of that temporal velocity leaks sideways into one of the 3 dimensions of space, and you are standing in the wrong place when it does, you will accelerate very quickly to your death. I have just described the true source of gravity. Don't look down. Every explanation you have ever heard runs the causation the same way round. Gravity is what slows clocks down. It is the other way around. The slowing of time is what makes things fall. By the end of tonight, you will know exactly how, and exactly how much of gravity is made of time. Before we begin, if you enjoy having a thing you thought was settled quietly turned around, a like or subscribe would mean a great deal. It is a small thing for you, and it keeps these going. Now, let's ease in. There is a china teapot hanging in empty space. It is a good teapot, white, with a fine blue line running around the rim. The kind of thing that would look completely unremarkable on a kitchen shelf and looks faintly ridiculous out here, thousands of light years from the nearest cup of tea. There is nothing near it, no planet, no star close enough to matter, no dust, no wind, no light, except the faint scatter of distant galaxies. It is not falling toward anything, because there is nothing to fall toward. It is not spinning. If you had carried it out there yourself and let go of it carefully, it would sit exactly where you left it, in exactly the orientation you left it, for as long as the universe lasts. That teapot is motionless. If you asked a room full of people to name the most motionless object anyone had ever described to them, that teapot would win. And it is traveling right now, this second, at the fastest rate anything in this universe is permitted to travel. I want to go slowly here, because this is the sentence the rest of tonight is built on, and if it slides past you, none of what follows will land properly. The teapot is not moving through space. That part is true, and I am not going to take it back. It has no velocity in any spatial direction. Nothing is carrying it anywhere. But space is not the only thing there is to move through. There is also time, and the teapot is moving through time. It is arriving at later and later moments, one after another, without pause, without any ability to slow down or stop or turn around, at a rate that turns out not to be arbitrary at all, but to be the maximum rate permitted to anything. You are doing the same thing. You are doing it right now. Whatever position you are lying in, however still you are holding yourself, however quiet the room is, every atom in your body is being carried forward through the time direction at full speed, and you have never once in your life been able to stop. Physicists have a particular way of drawing this, and it is worth building the picture in your head, because everything that follows lives inside it. Imagine a sheet of paper. Ordinarily, you would use the 2 directions on that sheet, left to right and up and down, to represent 2 directions of space. Tonight we are going to give one of them up. Keep left to right as a direction of space, and use up and down for time, with the future toward the top of the page. Now the teapot is a single point on that sheet. Because it is not moving through space, it does not drift left or right. But because it is moving through time, it climbs. A moment later, it is a little higher up the page. A moment after that, higher still. If you traced its whole history, you would get a perfectly straight vertical line running up the paper forever. That line is the entire biography of a teapot that never does anything. Your line is on that page somewhere too. So is the line of every atom in your body, and every atom in your bed, and every atom in the walls of the building around you. All of them climbing, none of them able to stop. Here is the part that turns this from a bookkeeping trick into something with teeth. In ordinary life, we treat motion through space and the passage of time as completely different categories. Space is where you go. Time is how long it takes to get there. They are separate kinds of thing, and they do not trade with one another. But that is not how this universe is put together. In relativity, space and time are not two independent things laid side by side, like two columns in a ledger. They are two aspects of one thing, and the ratio between them is not fixed by anything except how you happen to be moving, which means that motion through space and motion through time can be exchanged for each other. You already know one half of this, even if nobody has ever put it to you in these words. You have heard that a clock on a fast-moving spacecraft runs slow. That is not a malfunction of the clock. It is not an illusion produced by the signal taking time to reach you. It is the exchange happening. The spacecraft has taken some of its motion through time and redirected it into motion through space. It has less left over to spend on the time direction, so its clock ticks more slowly, and the faster it goes, the more of its temporal motion it has converted, and the slower the clock runs. There is a way of reading the mathematics of relativity that makes this exact, and it is used widely enough that you may have met it. I want to flag it as a reading rather than an unarguable fact, because it depends on a choice about how you write the equations down, and because it does not extend to everything, but within its territory it is precise. In that reading, everything, absolutely everything with mass, travels through space-time at exactly the speed of light. Not through space, through space-time. What differs from object to object is only how that fixed total is divided between the time direction and the space directions. Under that reading, a photon of light sits at one extreme. It travels through space at the speed of light, and so it has nothing left at all to spend on time. Its clock does not tick. It does not experience duration. Whatever is happening to a photon, it is not aging. And the teapot sits at the other extreme. It is not moving through space at all, which means that 100% of its allocation is going into the time direction. The teapot, sitting there doing absolutely nothing, is moving through time at the fastest rate anything can. It is the champion. Nothing in this universe is moving through time faster than an object that is completely at rest. So what about your body at this moment? More or less the same. Walking across a room at a little over 1 meter per second diverts such a laughably small fraction of your allocation into space that over an entire 80-year life, it costs you around 27 nanoseconds of elapsed time. 27 billionths of a second for a lifetime of walking. You would have to be moving at half the speed of light before the effect became large enough to argue about in ordinary language, and at that speed, your clock would be running at roughly 87% of the rate of a clock left behind. At 99% of light speed, it would be running at about 14%. At 99.9%, about 4.5%. The exchange is real at every speed. It is simply invisible at any speed a human body has ever reached, and very nearly invisible at any speed a human machine has ever reached. The fastest object we have ever built is a small spacecraft that has been repeatedly diving close to the Sun, and at its fastest, it was moving at about 190 kilometers per second. That is a genuinely enormous speed by the standards of anything that has ever come off a factory floor. It is about 6/10,000ths of the speed of light. Its motion through space, compared with its motion through time, is still less than 1 part in 1500. Even orbit barely moves the needle. An astronaut spent 340 consecutive days aboard the space station, going around this planet at about 7.5 kilometers per second, and came home roughly 5,000ths of a second younger than his identical twin brother, who had stayed on the ground. 5 milliseconds for a year in orbit. That is what the trade looks like when you push it as hard as human beings currently know how to push it. So hold on to that, because we are about to do something to it. We are going to put a mass nearby, not a large one by cosmic standards. A planet will do. And the moment we do that, something happens to the time direction itself. It stops being the same everywhere. It develops a slope. And an object that is already moving at full speed through a direction that has a slope in it does not simply carry on the way it was. But before I show you what happens, I have to convince you that the slope is real. Because it is going to sound like a mathematical device, the kind of thing physicists invent to make an equation come out neatly, and it is not. It has been measured. It has been measured in a tower in Massachusetts, on commercial airline flights, on a rocket, in the satellites that are talking to your phone right now, and most recently, inside a cloud of atoms 1 millimeter tall. That measurement history is where we are going next, and it is stranger than it sounds, because for more than 60 years, physicists have been chasing the same effect down to smaller and smaller scales, and what they have found is that there is no smallest scale. The slope does not begin somewhere. It is everywhere, all the way down, including between the top of your head and the soles of your feet. Cambridge, Massachusetts, 1959. There is a shaft running up through the middle of the Jefferson Physical Laboratory at Harvard, 22.5 meters from the bottom to the top, about 74 feet, the height of a 7-story building. Robert Pound and his graduate student Glenn Rebka have filled that shaft with a long mylar bag of helium, because ordinary air would scatter what they are about to send up through it, and there would be nothing left to measure at the far end. At the bottom of the shaft, there is a source of gamma rays from an isotope of iron, iron 57, at an energy of 14.4 thousand electron volts. At the top of the shaft, there is an absorber made of the same material. What they are trying to find out is whether those gamma rays arrive at the top with a very slightly different frequency from the one they left with. Not different by a percent. Not different by a part in 1,000. They are looking for a change of about 2.5 parts in 1,000 million. Written out, that is a 2, then a 5, then 14 zeros before you reach the decimal point on the other side. Try to hold what that means as a practical problem. If you wanted to detect a change that small in the pitch of a musical note, you would need to distinguish the note from itself after altering it by an amount that no instrument, no ear, and no recording device in existence in 1959 could have resolved. Not a difficult measurement, an impossible one, by the standards of the equipment available. They could attempt it at all only because of something discovered the year before by a young German physicist named Rudolf Nussbauer. He had found that atoms locked into a crystal lattice can emit and absorb gamma rays without recoiling, and the absence of that recoil makes the emitted spectral line astonishingly narrow. A narrow line is a sharp ruler. Nussbauer had done the work as a doctoral student on a problem his own supervisor considered unpromising. He received the Nobel Prize in Physics for it in 1961, at the age of 32. Pound and Rebka published their result in Physical Review Letters on the 1st of April 1960. The title was Apparent Weight of Photons. The prediction was 2.45 parts in 1,000 million. What they measured was 2.57, plus or minus 0.26, agreement to about 10%. 4 years later, Pound and a new collaborator, Joseph Snyder, tightened the same measurement to about 1%. 74 feet of altitude changes the rate at which time passes. That is what that experiment established, not as an interpretation of some data, as a reading on an instrument. Now watch what happens to the scale over the next 65 years, because the shape of the trend is the point. October 1971. Joseph Hafele and Richard Keating take 4 cesium beam atomic clocks and fly them around the world twice on regularly scheduled commercial airline flights, once heading east, once heading west. The clocks travel in booked passenger seats, like luggage that has paid for a ticket. The total budget for the experiment was somewhere in the region of $8,000, which even at the time was a remarkably small amount of money to spend on testing the structure of time itself. Going east, the prediction was that the flying clocks would lose about 40 nanoseconds, give or take 23. They lost 59, give or take 10. Going west, the prediction was a gain of about 275 nanoseconds, give or take 21. They gained 273, give or take 7. June 1976. A hydrogen maser is launched almost straight up on a rocket, climbs to an altitude of 10,000 kilometers, and falls back down. The experiment is called Gravity Probe A, and the results were published by Robert Vesso, Martin Levine, and their colleagues in Physical Review Letters in 1980. The measured shift agreed with the prediction to about 70 parts in a million. And then, quietly, the effect stopped being an experiment and became infrastructure. The satellite navigation system has been operating since 1978. Each satellite sits at an altitude of roughly 20,200 kilometers, carrying an atomic clock. Up there, higher out of the Earth's gravity, that clock runs fast relative to a clock on the ground by about 45 millionths of a second every day. But the satellite is also moving at about 3.9 kilometers per second, and that motion pulls the other way, slowing the clock by about 7 millionths of a second a day. The two effects do not cancel. The net result is a gain of about 38 millionths of a second per day. That number sounds trivially small until you remember what the system is actually doing. It is not measuring distances. It is measuring how long light took to travel from a satellite to the device in your pocket and multiplying by the speed of light. 38 millionths of a second of clock error multiplied by the speed of light gives a position error of somewhere between 10 and 11 kilometers per day. Every day, the system would be useless within about 2 minutes of being switched on and catastrophically wrong within an hour. So the correction is built into the hardware. The oscillators in those satellites are deliberately manufactured on the ground to run slightly slow at 10.22999999543 MHz, so that once they reach orbit and the local rate of time changes, they arrive at the 10.23 MHz the system actually needs. Engineers had to detune a clock at the factory to compensate for the shape of time above your head. There is a detail from the early days of that program that I find genuinely moving. The first generation of satellites shipped with a switch that could turn the relativistic frequency correction off. It was included because a portion of the engineering community was not convinced the correction would be necessary. They wanted the option to run the system without it and see. They ran it. It was necessary. The switch was never seriously used again. Then the instruments got better, and the scale of the measurement began collapsing inward. September 2010. A group at the National Institute of Standards and Technology in Boulder, Colorado, publish a paper in the journal Science with the almost defiantly plain title, Optical Clocks and Relativity. They resolve gravitational time dilation across a height difference of 33 centimeters, about the height of a stack of books on a desk. In the same paper, they resolve velocity time dilation at speeds of around 10 meters per second, which is roughly the pace of a sprinter. February 2022. A team at a joint institute in Boulder publish in Nature. They take a cloud of ultra-cold strontium atoms 1 millimeter tall and resolve the change in the rate of time from the bottom of that cloud to the top. 1 millimeter, the width of a grain of coarse sand. Their fractional frequency uncertainty was 7.6 parts in 100,000 million. July 2024. The same institute pushes the systematic uncertainty of a strontium lattice clock to 8.1 parts in 10,000 million, sensitive to altitude changes of roughly 1 centimeter. July 2025. A team in the same city unveils a clock built around a single aluminium ion, cooled by one co-trapped magnesium ion, with a systematic uncertainty of 5.5 parts in 10,000 million. It is the most accurate clock that has ever existed, 19 decimal places, and it is so accurate that the height of the table it is standing on is a significant correction to its output. If you picked it up and moved it to a shelf, you would have to recalculate. Look at the shape of that list. In 1960, you needed a 7-story building. In 2010, you needed a stack of books. In 2022, you needed a millimeter. In 2025, you need to know which shelf. That is not merely a story about instruments improving. It is telling you something about the thing being measured. There is no boundary anywhere. There is no altitude at which the rate of time switches from one value to another. The rate of time varies continuously, smoothly, without gaps, at every scale anyone has ever managed to look at. And every time we look at a smaller scale, it is still there. Which means it is there between the top of your head and the soles of your feet. Right now, near the surface of this planet, the rate of time changes by roughly 1 part in 10,000 million for every meter of height. A person about 1.7 meters tall who spends their life standing up will, over the course of 80 years, accumulate something like 470 nanoseconds less elapsed time at their feet than at their head. Your feet are younger than your head, not by much, but measurably and permanently, and there is nothing you can do about it. So the slope is real. It has been dragged out of theory and into hardware, and then into a single cubic millimeter of cold atoms. That much is settled, and it still does not explain a single thing about why anything falls. A clock running slow is not a force. It does not push. It has no direction of push to offer. So before we can go anywhere near the mechanism, there is a prior question that needs answering. Why does this happen at all? Why should the presence of a planet have anything whatsoever to do with the rate at which a clock ticks? The answer to that one was worked out before any of these experiments were possible, before anyone had an instrument capable of detecting the effect at all. It was worked out in 1911, in an argument that required no equipment whatsoever. In 1911, 4 years before he had a complete theory of gravity, Einstein published a short argument that did not require a single instrument. It required a room. Imagine a sealed box with no windows, drifting far from any star. Inside it, a person floats. Nothing has weight. Objects released simply hang where they were let go. Now attach a rope to the top of that box and start hauling it upward with a steady acceleration. Let us say 9.8 meters per second squared, which is the rate at which things speed up when you drop them near the surface of this planet. Immediately, the person inside stops floating. They settle onto what is now unmistakably the floor. Objects released fall. They fall in exactly the way objects fall on Earth, at exactly the same rate. And if you drop a hammer and a feather in the same instant inside that box, with no air in it, they land together. Einstein's claim was that there is no experiment the person inside the box can perform to tell whether they are being accelerated through empty space or standing still in a gravitational field. Not that it is difficult to tell, that it is impossible in principle, as long as you stay local. As long as the box is small enough and the experiment quick enough that you cannot detect the way a real gravitational field converges toward the center of a planet. That is the equivalence principle, and it has been tested about as hard as anything in physics has ever been tested. The modern version compares how differently constituted objects fall. If gravity and acceleration are truly the same thing, then everything must fall identically, regardless of what it is made of, because acceleration does not care what an object is made of. A satellite mission, whose final results were published in 2022, compared free-falling test masses of titanium alloy and platinum alloy in orbit, and found no difference in how they fell, down to a level of about 1 part in 1,000 million million, 15 decimal places, and no crack anywhere in it. That mission ran for 2.5 years and accumulated about 5 months of usable free-fall data, 2/3 of it with the 2 different alloys, and the final third with a matched pair of identical platinum masses as a control, so that any signal in the mismatched pair could be checked against a pair that should show nothing. The test masses were held in place by electrostatic forces, and what was actually recorded was how much force each one needed in order not to drift. If titanium and platinum were falling even fractionally differently, that difference would have shown up as a mismatch in the electrostatic effort required. It did not. Ground-based groups using torsion balances have been closing on the same answer from the other direction for decades, and they too keep finding nothing at ever finer precision over ever shorter ranges. I want to be clear about why this matters so much, because it can look like a technicality. If different substances fell differently, gravity could not be encoded in the geometry of a place at all. You would need one geometry for titanium and another for platinum, which is not a geometry. It is a force with a very good disguise. The fact that everything falls identically is what makes the geometric description possible in the first place. It is the permission slip for the entire picture we are about to build. Now watch what the equivalence principle does to time, because this is where the argument gets pointed. Put a light source at the floor of the accelerating box and a detector at the ceiling. Fire a pulse upward. The light takes a small but genuinely non-zero amount of time to cross the box. During that crossing, the box is accelerating, so by the time the pulse reaches the ceiling is moving faster than it was when the pulse was emitted. The detector is running away from the incoming light, which means the light arrives redshifted. Its frequency is lower than the frequency it left with. This is just the Doppler effect. It is the same reason a receding ambulance sounds lower than an approaching one. There is nothing exotic about it, and nothing about it depends on relativity being true. It depends only on the ceiling having picked up speed while the light was in transit. Now apply the principle. If the person inside cannot distinguish that accelerating box from a box sitting still in a gravitational field, then the exact same redshift has to occur in the gravitational case. Light climbing away from a mass has to arrive with a lower frequency than it left with. And frequency is a clock. That is not a metaphor, and it is not a loose analogy. A frequency is a count of cycles per second, and a cycle is the tick of an oscillator. If a signal generated by 1,000 million cycles at the floor is received as very slightly fewer than 1,000 million cycles at the ceiling, then the floor's second and the ceiling's second are not the same length. The floor's clock is running slow. That is the whole argument. It requires nothing but the equivalence principle, the Doppler effect, and a refusal to tolerate inconsistency. Once you accept that being accelerated and being in a gravitational field are locally the same situation, gravitational time dilation is not a discovery. It is a consequence. It follows as unavoidably as 1 + 1 making 2, which means that Pound and Rebka were not, strictly speaking, testing whether the effect exists. They were testing whether this universe is consistent. It was. And this is the exact point at which I have to take the satisfaction away again, because I think this is where almost every explanation of this subject quietly stops, and where the actual question begins. We now know that gravity must slow clocks, on the grounds of logical consistency. We know that gravity does slow clocks, on the grounds of about 10 separate classes of experiment across 65 years. What we have not been told, what I have not told you, and what the equivalence principle argument does not contain anywhere inside it, is why or how that slowing has anything to do with an apple leaving a branch. Think about how strange that gap is. You have a room in which clocks at the floor tick slightly slower than clocks at the ceiling. Fine. Now explain to me. Using only that fact, why a dropped pen accelerates toward the floor at 9.8 meters per second squared. A slow clock is not a force. It does not push. It has no direction. There is nothing in the statement this clock ticks at a slightly different rate from that one that obviously has anything at all to do with a lethal acceleration toward the ground. It is worth pausing on how long that gap has been sitting there in plain sight. The observation that everything falls at the same rate regardless of what it is made of is very old. It is the observation Galileo is supposed to have tested from a tower in Pisa, and which an astronaut demonstrated for real on the surface of the Moon in 1971 by dropping a geological hammer and a falcon feather in front of a television camera. They hit the lunar dust together. A Hungarian physicist named Laurent Eötvös spent decades around the turn of the 20th century measuring the same equivalence with torsion balances to a precision of a few parts in 1,000 million, and his successors have been narrowing that number ever since. But knowing that all objects fall identically tells you nothing whatsoever about why any of them fall at all. It only tells you that whatever the cause is, it cannot be interested in what things are made of. That is a strong clue, and Einstein read it correctly. A cause that is completely indifferent to composition, to charge, to temperature, to internal structure, to chemistry, is not behaving like a force. Electromagnetism cares enormously what you are made of. So does the strong nuclear force. Gravity does not check, which suggests that whatever is happening is not happening to the object at all. It is happening to the place the object is in. There is one more thing to notice before we move, because it is going to matter later. A uniform slowing of time, the same everywhere, at every altitude, by the same factor, would do absolutely nothing. It would not produce weight, or falling, or any observable effect whatsoever. It would simply be a relabeling of what we choose to call a second. Nothing in physics depends on the absolute rate of time. Everything depends on the difference in rate from one place to the next. So the thing we are looking for is not slowness, it is slope. And we are still not ready to say what that slope does. We have established that it exists, that it has been measured down to the width of a grain of sand, and that it follows necessarily from an argument a person could have made in an empty room in 1911. What we have not established is the one thing that matters. We have not established how a difference in the rate of a clock between here and 1 meter lower turns into motion. Before we can get there, I have to fix a sentence. It is a sentence you have almost certainly heard, and it is in the wrong order. Here is the sentence you have heard. Gravity slows down time. It is in every documentary. It is in every textbook aimed at people who are not going to become physicists. It is the reason you know the phrase gravitational time dilation at all. And as a description of what an instrument reads, it is completely correct. Put a clock at the bottom of a tower and a clock at the top, and the one at the bottom will run slow. Gravity slowed it. Nobody is disputing the measurement. But as a description of what causes what, it is backwards. Gravity does not warp the flow of time. The warping of time is what produces gravity. I want to sit inside that for a minute, because I know how it sounds. It sounds like wordplay. It sounds like the kind of reversal people reach for when they want to make an ordinary idea seem profound. It is not. It is a statement about which quantity in the actual mathematics is doing the work, and the answer is not the one you were taught. Think about the picture you have been carrying. It probably runs something like this. Mass exists. Mass creates gravity. Gravity bends space-time. Bent space-time does various interesting things, including slowing clocks. On that picture, the clock slowing sits at the far end of the chain. It is a consequence, a downstream curiosity, something that shows up in satellite corrections and science documentaries and does not really have anything to do with the business of falling. Now here is the chain, as general relativity actually has it, in the regime that covers essentially everything you will ever experience. Mass and energy exist. Their presence changes the rate at which time passes nearby, more slowly closer in, less slowly further out, continuously, with no boundary. And that difference in rate, that slope, is what makes things fall. It is not a consequence of gravity in the everyday regime. It is the entirety of gravity, not part of it, not the interesting half, essentially all of it. I will show you what the equation says about this in a few parts' time, and I will show you exactly how much of the effect the time slope accounts for, and where that stops being true, because there is a boundary, and it is one of the most beautiful things in this whole subject. But I want to state the claim in its strongest form first, so that you can feel how much weight it is carrying. When you drop a stone, nothing pulls it, nothing pushes it. There is no force acting on it, and I mean that in the technical sense, as well as the poetic one. An accelerometer taped to that stone reads 0 for the entire duration of its fall. It reads 0 at the moment of release. It reads 0 1 meter above the floor. It reads 0 right up until the impact, at which point it reads a very large number, because the impact is the only event in the whole sequence that involves a force at all. The stone is not being acted upon. The stone is doing exactly what it was doing before you let go, moving forward through time. That is all. It has not changed its behavior in any way. What changed is that when it was in your hand was holding it off the path that motion naturally takes here. When you opened your fingers, it went back to that path, and the path bends downward, because time runs slower down there. Now turn that around and point it at yourself, because the consequence is stranger than the statement. If a falling object has no force acting on it, then you, sitting or lying there perfectly still, not falling at all, are the one in the unusual situation. You are the one being acted upon. The chair, the mattress, the floorboards, the joists, the foundations, the crust of this planet. Something solid is pushing upward on you continuously, and has been for your entire life, in order to keep you off the path you would otherwise be taking. An accelerometer, resting on your chest right now, would read 9.8 meters per second squared, straight up. Which means something that took me an embarrassingly long time to accept. You have never felt gravity. Not once. Not in your entire life. In free fall, the one situation in which gravity is unambiguously the only thing going on, you feel nothing at all. That is what astronauts are describing when they talk about weightlessness, and it is not because they have escaped this planet's gravity. The space station is only about 400 kilometers up, where the Earth's gravitational pull is still around 90% of its surface value. They feel nothing because falling feels like nothing. It has always felt like nothing. It is the only thing in physics that feels like nothing. What you have felt every waking second is the floor. I find it useful to notice how thoroughly the instrument agrees with this, because an accelerometer is not a philosopher and has no opinion about what gravity is. There is one in the phone beside you. It is a tiny piece of silicon with a small mass suspended on flexible arms, and it reports how hard those arms are having to work to keep that mass in step with the rest of the device. Sitting on a table, it reports 9.8 meters per second squared, upward. Drop the phone, and, for the fraction of a second before it lands, the arms relax, and the reading drops towards 0. That is the whole basis of the free fall detection that some phones use to sense they are falling. The device is not detecting an absence of gravity, it is detecting the absence of a floor. And if you have ever been in an aeroplane that dropped suddenly through a pocket of unstable air, you have had a brief, unpleasant taste of the same thing. The sensation people describe as their stomach lifting is not gravity increasing or decreasing. It is the floor of the cabin briefly stopping its work. This is why the phrase gravitational attraction is, strictly speaking, a piece of 17th century vocabulary that we have simply never got round to replacing. Attraction implies a pull. It implies something reaching across a distance and exerting an influence on a body that would otherwise have stayed put. Newton himself was famously uneasy about it. In a letter to Richard Bentley in 1693, he called the idea that one body could act upon another at a distance through a vacuum, without anything in between, so great an absurdity that he believed no competent thinker could ever accept it. He wrote down the law anyway, because the law worked, and he left the mechanism to posterity. Posterity took 228 years, and then answered him. There is no action at a distance. There is no reaching across. There is only geometry, and the geometry is mostly made of time. It is worth remembering how well Newton's version worked in the meantime, because the point is not that he was foolish. His law predicted the return of a comet. It predicted the existence of a planet nobody had seen. It gave the shape of this planet, the timing of the tides, and the orbits of the moons of Jupiter. For 2 centuries, the only visible flaw in the entire structure was a discrepancy of 43 seconds of arc per century in the precession of Mercury's orbit. An error so small that the leading explanation for decades was an undiscovered planet closer to the Sun, provisionally named Vulcan, which people spent years looking for and never found. That 43 seconds of arc is the size of the crack that the whole of general relativity came out of. Everything else Newton wrote about gravity was numerically near enough perfect. What was wrong was not the arithmetic. What was wrong was the story about what the arithmetic described. Let me put some numbers on how mostly, near the surface of this planet, of the total curvature of space-time that a slow-moving object samples as it falls, the temporal component, the part encoding how fast clocks tick, accounts for essentially the whole of the observed acceleration. The spatial component, the actual bending of space itself, contributes a correction so small that for anything moving at ordinary speeds, it is completely unmeasurable. The bowling ball on a rubber sheet image that most people have in their heads is a picture of that spatial part. It is a picture of the negligible half. The half that does the work is not shown at all, because it is not a shape you can draw with a stretched sheet. It is a variation in the rate of a quantity that a sheet does not have. So the most famous visualization of gravity in the world depicts the wrong component. I will come back to that, and I will come back to it with some feeling, because the rubber sheet has done more damage to public understanding of this subject than any other teaching aid in physics. But before any of that, the mechanism, because I have now claimed twice that a slope in the rate of time produces a downward acceleration, and I have not given you a single reason to believe it is even possible. A gradient in clock rates still does not push. It still has no direction of shove to offer. So how, physically, does a difference in the rate of time between here and 1 meter lower turn into motion? The answer requires you to stop thinking of the slope as a fact about clocks and start seeing it as a shape, something with a direction, something that a moving object can be inside of. So let us build it. Let us go back to the sheet of paper with the teapot on it. One direction across for space, one direction up for time. And let us put a planet on it. Not the planet as a globe. We have given up 2 of the 3 spatial directions to make room for time, so the planet appears on the page as a band, running vertically. The history of a thing that stays where it is. What matters is not the band. What matters is what happens to the page around it. Fill the space around that band with clocks. Identical clocks. Thousands of them, an even grid of them, spreading out in every direction from the planet's surface, each one ticking, each one climbing the page as it ticks, because ticking is what moving through time looks like on this diagram. Now watch them for a while, and something becomes visible that no single clock could ever have shown you. They are not climbing at the same rate. The ones furthest out are moving up the page fastest. For every one tick of the clocks near the surface, the distant ones have managed slightly more. Not dramatically more. Near this planet, the difference is about 1 part in 10,000 million per meter, which over the whole height of the atmosphere adds up to something you would need a laboratory to detect. But the pattern is unmistakable once you can see the whole field at once. Far away, time runs quickly. Close in, it drags. And there is no boundary anywhere. That is the thing to hold on to. There is no altitude at which the clocks switch from one rate to another. There is no shell, no membrane, no place where fast time stops and slow time begins. Every clock in that field is running at a rate very slightly different from its immediate neighbors, in every direction, all the way in and all the way out. It is a smooth, continuous variation, and we have now measured it across a millimeter of cold atoms, which tells us it continues below any scale we have yet been able to probe. I want you to stop seeing this as a fact about clocks. Clocks are just the instruments. Clocks are how we found out. What is actually there is a shape. Try it this way. You are standing beside a river on a still afternoon. Out in the middle, the water is moving quickly. You can see it, the surface pulling into little ridges, a leaf carried along at something like walking pace. Near the bank, the same river is barely moving at all. The bed is shallower there, and the water drags against it, and against the reeds, and against the stones. If you dropped a leaf near the bank, it would take a minute to travel the distance a mid-river leaf covers in a second. It is one river. There is no line down the middle, where the fast water stops and the slow water starts. There is a continuous variation in speed from the center to the edge, and every part of the flow is moving at a slightly different rate from the part immediately beside it. That is the shape of time around a mass. Not a substance flowing, a rate varying, quickly out in the empty middle distance, dragging as it comes in close, and continuous everywhere in between. A planet's mass behaves like a shallow bed, or a bank, or a stand of reeds. It does not stop the flow, it drags on it. Now, let me widen the picture, because this planet is a very gentle example, and the shape gets much more pronounced elsewhere. On the surface of the Sun, clocks run slow, relative to deep space, by about 2 parts in a million. That comes out at roughly 66 seconds a year. A white dwarf, a star that has packed something close to the mass of the Sun into a body about the size of the Earth, drags harder, a few parts in 10,000. The first person to attempt that measurement was an astronomer at Mount Wilson in 1925. Looking at the faint companion of the brightest star in the night sky, and his numbers were badly contaminated by scattered light from the bright star next to it. It took until the era of space telescopes to get it properly right. On the surface of a neutron star of 1.5 times the mass of the Sun, squeezed into a sphere 12 kilometers across, the drag is no longer a correction. Clocks there run at about 80% of the rate of distant clocks. A century out here is 80 years down there. That is not a subtlety you need an atomic clock to see. You could measure it with a wristwatch and a calendar. And at the horizon of a black hole, the drag reaches its limit. The rate of time, relative to a distant observer, falls to 0. Not slow. Stopped. That is what a horizon is in this language. The surface where the stream, as seen from outside, ceases to move at all, and where the idea of hovering in place, of holding yourself at a fixed height off the path, stops being purchasable at any price, with any engine, by anything. Same shape, same rule, different steepness. This planet is simply the shallowest example any of us will ever stand on. It is worth registering that none of those steeper examples are hypothetical. The slowing at a neutron star's surface is read directly out of the light we receive from them. When a neutron star's surface flares in an X-ray burst, the spectral lines in that light arrive shifted in a way that encodes how slowly time was running where they were emitted, And that shift is one of the very few handles anyone has on what the matter inside a neutron star is actually doing. And the region where the rate of time falls all the way to zero is not microscopic either. The black hole at the center of this galaxy has a horizon roughly 12 million kilometers across, which is comparable to the orbit of Mercury. That is a volume the size of the inner solar system in which the stream has stopped. Now, if you have been listening carefully, you have already spotted the obvious consequence, and you have probably also spotted that it cannot possibly be the whole story. The obvious consequence is that different parts of an object age differently. The top of a tree is running its life very slightly faster than the roots. The upper floors of a building are marginally ahead of the lobby. Your head is ahead of your feet by about 470 nanoseconds over a lifetime, and if you spend most of your life sitting down, rather less than that. That is true. It is measured, but it is trivia. It changes nothing. If that were the only consequence of the gradient, the whole business would be a footnote in a physics textbook, and nobody would ever have built a satellite navigation system around it. The reason it is not trivia is that objects are not passive. An object sitting in this field is not a static thing having something done to it. It is moving, remember, through the time direction, at the maximum possible rate, continuously, without pause, and the time direction is the very thing that is varying. So the question is not what happens to a stationary object in a gradient of time. There are no stationary objects. The question is, what happens to something already traveling at full speed through a direction that is not the same from one place to the next? To answer that, I need one more piece, and it is the piece that makes the whole thing work. An object is not a point. A teapot is made of somewhere in the region of 10 to the power of 25 atoms, and each one of those atoms is, in effect, its own tiny clock, trying to tick at its own local rate. The atoms in the base of the teapot are marginally deeper in the slow region than the atoms in the lid. Each of them, considered alone, would climb the page at its own slightly different rate. But they are not alone. They are bolted together into one object by the electromagnetic forces that hold the china rigid. The teapot does not get to have 10 to the power of 25 different rates of progress through time. It is one thing. It has one motion through space-time. So what is the motion of the whole? Not the average. Exactly. Something more interesting than an average. Because in relativity, motion through time and motion through space are not independent quantities that can be tallied separately. They are components of a single direction, a single arrow pointing through space-time, which physicists call the four-velocity, and whose length never changes. Only its direction can change. And an arrow whose two ends are being carried at different rates does not stay pointing where it was. Leave the physics alone for a moment. We are going back to the river. It is late afternoon, and the light is low. There are two rowing boats on the water, both drifting, neither of them under oar. One of them is out in the middle of the channel, where the current runs fast, and it is being carried downstream at a decent walking pace. The other is close to the bank, in the slow water, where the reeds drag and the bed comes up shallow, and it is barely moving at all. They come alongside each other, more or less, the fast boat gaining. The person in the slow boat, near the bank, holds out an oar. The person in the fast boat reaches out and takes hold of the end of it. Now stop. Before I tell you what happens, ask yourself what you expect. Most people's instinct here is right, and it is worth trusting. The moment those two boats are connected, they stop being two objects with two different velocities and become one object. An awkward, extended, roughly rigid thing, about 3 meters of oar with a boat at each end, drifting downstream. And that one object has a problem, because its two ends are being carried at different speeds. The end out in the channel wants to go faster than the end by the bank. It cannot. It is one object now. So the difference resolves itself the only way it can. The joined thing rotates, the fast end swings around, the slow end acts as a pivot, and the overall direction of travel of the pair tips toward the bank. The fast boat gets pulled toward the shore. Nothing pulled it. Nobody rowed. No force reached across the water and dragged it sideways. What happened is that a rigid object was placed into a flow whose speed varied across its length, and the variation in speed across its length rotated its direction of travel toward the slow side. That is the mechanism. That is the whole mechanism. Everything else is bookkeeping. Notice how little the mechanism needs in order to work. It does not need a source of force. It does not need anything to be transmitted from one place to another. It does not need the two boats to know anything about each other, or about the river, or about how far away the bank is. All it needs is a flow whose rate varies across a distance, and an object spanning that distance which has no choice but to keep moving. Now take the river away and put space-time back. You have an object. The teapot, a stone, a person, whatever you like. It is made of an enormous number of tiny constituents, each one of which has its own motion through time. Right now, before we put a planet anywhere near it, they all have exactly the same motion, straight up the page, at the maximum rate, all of them parallel, all of them in perfect agreement. The object's overall direction of travel through space-time, its forward velocity, that single arrow of fixed length, points straight along the time axis and nowhere else. The object is at rest in space, and it is moving through time as fast as anything ever moves through anything. Now, put a planet underneath it. Immediately the constituents stop agreeing. The ones at the bottom of the object are in slower time. The ones at the top are in faster time. Each one on its own would climb the page at its own rate, the bottom ones lagging very slightly, the top ones running very slightly ahead. But they are not on their own. They are one object, and an object has one forward velocity, one arrow, one direction of travel through space-time. So the same thing happens that happened to the boats. The mismatch across the object's length resolves itself by rotating the arrow, and it rotates it in the direction of the slower flow, because the slow end is the end that drags, the end that pivots, the end the whole thing swings toward. The slow end is the end nearest the planet. The arrow tips downward. That is falling. That is the entire phenomenon. The object's forward velocity, which started out pointing purely along the time axis, has been rotated so that a sliver of it now points along a spatial axis, specifically the axis pointing toward the mass. And an object whose direction of travel through space-time has a spatial component is, by definition, moving through space. And it keeps happening. The object is now marginally lower than it was, which means it is in a marginally steeper part of the gradient, which rotates the arrow a little further, which moves it a little faster, which takes it lower still. The rotation compounds. The spatial component grows. The object speeds up. That is acceleration. That is why a dropped stone does not fall at a constant speed, but gets faster and faster all the way down, at 9.8 meters per second squared, adding another 9.8 meters per second to its speed with every second that passes. It is not being pushed harder as it goes. It is being rotated further as it goes. And notice what this explains for free, something Newton's version could only state as a brute fact. Why does everything fall at the same rate? Why do a hammer and a feather, dropped together on the airless surface of the moon, hit the ground at the same instant, despite one of them being thousands of times more massive than the other? In the Newtonian picture, this is a coincidence, and a suspicious one. The heavier object is pulled harder, but it is also harder to move, and the two effects happen to cancel exactly, always, to every decimal place anyone has ever measured. Newton had no explanation for why the mass that determines how strongly you are pulled should be the same number as the mass that determines how hard you are to shift. He simply observed that it was. and moved on. In the picture we have just built, there is nothing to explain. The rotation is a property of the region, not of the object. The gradient of time, at a given place, is whatever it is. It does not consult the object about its mass before rotating it. A hammer and a feather, in the same place, are subject to the same slope, so they rotate at the same rate, so they fall together. Composition is irrelevant. Weight is irrelevant. The only thing that matters is where you are. That is why the equivalence principle from part 3 is not an axiom that has to be imposed on the theory from outside. It falls out of the geometry automatically. Einstein did not have to assume it twice. He assumed it once, built a geometry on it, and got it back for free at the other end. I want to be careful about one thing here, because it is the point at which a good analogy can quietly turn into a bad one. The boats and the oar are a picture, not a proof. The rotation in the river is a real mechanical torque, transmitted through a wooden shaft, and the wood is under stress. You could measure that stress. You could break the oar if the current were strong enough. That is not what is happening in the space-time case. There is no stress in a freely falling object. That is exactly why an accelerometer inside it reads 0. Nothing in the object is being strained or twisted. The rotation of the four-velocity is not a mechanical event happening to the object. It is a geometric consequence of what the object's motion means in a region where the time direction is not uniform. And if you want the honest version, and we are going to do the honest version properly in a couple of parts' time, the object does not need to have any size at all for this to work, because the mathematics is written in terms of derivatives, and a derivative is defined over an infinitesimal separation. The extended object picture is how you see it. The derivative is what is actually there. But hold the picture anyway, because the picture is correct about the thing that matters. A difference in the rate of time across a small separation rotates the direction of motion toward the slower side. That is the physical content. Whether you get there by imagining a teapot straddling a gradient or by writing down a partial derivative, the answer that comes out is the same. And it is a downward acceleration of 9.8 meters per second squared at the surface of this particular planet. There is a version of this same idea that turns up in ordinary fluid mechanics, and it is not a coincidence. Drop a short, rigid rod into a flow that is moving faster on one side than the other, and the rod rotates, at a rate set by how quickly the flow speed changes across it. Engineers who work with suspensions of small fibers in moving liquids calculate this routinely. It is the same geometry doing the same thing. The only difference in the gravitational case is that the flow is not a substance, and the rod does not have to exist. Now here is the thing I have not yet mentioned, and it is the part that turns this from an elegant explanation into something with genuine menace. That arrow has a fixed length. It cannot get longer. Its magnitude is always the same, no matter what the object does. So when a sliver of it rotates into the spatial direction, that sliver has to come from somewhere. It comes out of the time component. The object buys its motion through space by giving up motion through time. It falls, and in exchange, its clock runs slower. And once you ask what the exchange rate is, this stops being a piece of geometry and starts being genuinely alarming. Let us stop for a moment and put the pieces we have on the table in order, because we are roughly halfway through and everything from here builds on them. 1. Nothing is ever at rest. An object sitting still is traveling through the time direction at the maximum rate anything can travel, and its total motion through space-time has a fixed magnitude that can be redistributed but never increased. 2. Near mass, the rate at which time passes varies continuously with position, slower closer in, faster further out, with no boundary anywhere, measured now from a 74-foot tower all the way down to a millimeter of cold strontium. 3. An object placed in that gradient has its direction of travel through space-time rotated toward the slower side. In the same way, two boats joined by an oar in a river with a varying current swing toward the bank. 4. That rotation is falling. The object acquires a component of motion in space, aimed at the mass, and that component grows as it descends into a steeper part of the gradient. And 5, which is where we now go. The rotation is a redistribution, not an addition. The arrow's length does not change. Every scrap of motion the object gains through space is taken out of its motion through time. So let us do the accounting, because the numbers are absurd. Here is the entire physical input to everything I have described. Near the surface of this planet, the rate at which time passes changes with height by an amount equal to the local gravitational acceleration divided by the speed of light squared. Work that out, and you get a figure of roughly 1 part in 10,000 million per meter. Try to hold the size of that. Take a clock at your feet and a clock at your head. Over 1 meter of separation, their rates differ by about 1 part in 10 million. A difference so small that until 1960, nobody on this planet had an instrument capable of detecting it in a laboratory, and until 2022, nobody could see it change across a distance smaller than a bookshelf. And out of that difference, the universe manufactures a 9.8 meters per second squared acceleration. It manufactures the weight you can feel pressing you into whatever you are lying on. It manufactures the reason a dropped mug shatters, the reason bridges need engineering, the reason falling from a great height kills you. All of it comes out of a rate difference of 1 part in 10,000 million per meter. That is the exchange rate, and it is monstrously lopsided in favor of space. The reason it is so lopsided is a factor you already know. When motion is traded between the time direction and the space directions, the conversion constant is the speed of light. And because of how the geometry works, the relevant factor when you convert a time rate difference into a spatial acceleration is the speed of light squared. That number, in ordinary units, is about 90,000 million. It is an enormous multiplier, and it sits between two quantities that would otherwise seem to have nothing to do with each other. You have met that multiplier before, doing exactly the same job. In the most famous equation in physics, the one relating energy and mass, the speed of light squared is the exchange rate between the amount of matter you have and the amount of energy it corresponds to. That is why converting an almost invisible quantity of mass releases an appalling amount of energy. Why a few kilograms of material can level a city. It is not that mass is secretly full of energy in some mystical sense. It is that the conversion factor between the two currencies is very, very large, and so a tiny amount of one buys an enormous amount of the other. The falling case is the same trade, in a different direction. A teapot exchanges an utterly imperceptible slowing of its clock for a rapid plummet toward the floor. The teapot loses almost nothing in the currency of time and gains a great deal in the currency of space, because the speed of light stands between the two columns of the ledger, and it is very large. And you can check this by hand, which I find satisfying. Take the speed of light squared, about 9 followed by 16 zeros. Multiply it by the rate gradient, about 1.1, preceded by 16 zeros after the decimal point. The two enormous numbers annihilate each other, and what is left over is 9.8. That is not an analogy or an approximation. That is where the 9.8 comes from. I said near the beginning of tonight, lightly, don't look down. I would like to withdraw the lightness now. You are moving through time at the maximum rate anything moves through anything. That motion is not stored somewhere safe. It is available, and it is convertible. And the conversion rate is such that a change in your temporal velocity, too small to measure with any wristwatch ever built, corresponds to a spatial velocity large enough to end you. Right now, The only thing preventing that conversion from proceeding is the flaw. Remove the flaw, and the trade begins immediately, and the arithmetic is not in your favor, and it never was. That is what it means to say that gravity kills people. It is not a force overwhelming you. It is a currency exchange, running in a direction you cannot stop, at a rate you did not set. Now, since the trade is real, we should be able to see the other side of it. The payment. A falling object should be losing time. It is. And the amount is unmeasurable for that object alone. Over the couple of seconds of a fall from a first-floor window, the accumulated difference is a fraction of a nanosecond, far below anything any instrument could detect. Put some concrete numbers on that, because the asymmetry is the whole point. A fall of 10 meters takes about 1.5 seconds and gets you to roughly 14 meters per second by the end of it, which onto a hard surface is comfortably lethal. The proper time that fall costs the falling body is somewhere around 1 part in 10,000 million of a second. A body falling freely through air for long enough to reach terminal velocity, which is about 55 meters per second face down and can approach 90 head down, is still only paying in the currency of nanoseconds. The entire lethality of the event lives on the spatial side of the ledger. The temporal side barely notices that anything has happened. But integrate the same effect over a long enough stretch, and it becomes something you can put on a page. A person who spends 80 years at the surface of this planet accumulates about 1.8 seconds less elapsed time than a clock sitting far away from any mass at all. Not 1.8 seconds per year. 1.8 seconds across an entire life. That is the total bill for 8 decades of being held at the bottom of a gravitational well. And the head-to-feet difference over that same lifetime is about 470 nanoseconds. 0.5 millionth of a second. Those are the numbers. That is the size of the thing that produces every gravitational phenomenon you have ever witnessed. 1.5 seconds over a lifetime. 0.5 millionth of a second between your scalp and your soles. For comparison, the velocity side of the same ledger is even smaller at human speeds. Walking around at a bit over 1 meter per second for 80 years costs you around 27 nanoseconds, roughly 17 times less than the head-to-feet gravitational effect. Even an astronaut does not do much better. 340 consecutive days in orbit, at 7.5 kilometers per second, returns you about 5,000ths of a second younger than the twin brother you left behind. 5 milliseconds for a year of the fastest sustained travel any human being has managed. The trade is real at every scale. It only becomes visible when the numbers get extreme. There is something almost insulting about the scale mismatch. The most physically consequential feature of life on the surface of a planet, the thing that decided the shape of every organism that ever evolved here, the thing that limits how tall a tree can grow, and how large a land animal can get, and how fast a heart has to beat to push blood upward against it, comes out of a discrepancy at the 15th decimal place. But I have been doing something slightly unfair for the last 2 parts, and it is time to fix it. I have been persuading you with a picture. Boats, oars, rivers, arrows, a teapot straddling a gradient. Pictures are how understanding starts, but they are not evidence, and a good picture can be completely wrong. So let me show you what the mathematics actually says. Not because you need to do the mathematics. You do not, and I am not going to put a single symbol in front of you tonight, but because I want you to know that the picture I have given you is not a simplification of the real answer. It is the real answer. General relativity has a rule for how anything moves when nothing is pushing it. It is called the geodesic equation, and I want to walk you through what it says in ordinary words, because the structure of it is the whole argument. The rule says this: take an object that is not being pushed by anything, no rocket, no rope, no floor. The rate at which its direction of travel through space-time changes is determined by two things: the geometry of the region it is passing through, and the object's own direction of travel through space-time. And here is the crucial structural detail. The object's own direction of travel enters that calculation twice. Not once, twice, multiplied together. That doubling is where everything comes from. So let us take it slowly. The geometry of a region of space-time is described by a set of quantities that tell you how much curvature there is and in which combinations of directions. Some of those quantities describe how the time direction changes from place to place. Some describe how the space directions change. Some describe mixed cases, how time changes as you move sideways, how space changes as you move forward in time, and so on. There are 10 independent numbers in total describing the geometry at a point, and the rule for motion involves all of them, but not equally. Each of those geometric quantities gets multiplied by two components of the object's direction of travel. A quantity describing pure time curvature gets multiplied by the object's time component twice. A quantity describing pure space curvature gets multiplied by the object's space component twice. A mixed quantity gets multiplied by one of each. Now put in a real object: a dropped stone, a person stepping off a curb, a planet in orbit, anything moving at the sort of speeds that exist in ordinary life. What does its direction of travel through space-time look like? We established this in part 1. It is almost entirely in the time direction, overwhelmingly. A person walking has a spatial component that is about 1 part in 300 million of their temporal component. A commercial airliner, about 1 part in a million. Even the fastest object human beings have ever built, at its closest approach to the sun, moving at about 190 kilometers per second, has a spatial component that is less than 1 part in 1500 of its temporal one. So now go back through that list of geometric quantities and multiply them by the appropriate components. The pure space curvature terms get multiplied by a tiny number, twice. Tiny multiplied by tiny is negligible beyond negligible. Those terms vanish. The mixed terms get multiplied by a tiny number once, still negligible. The pure time curvature term gets multiplied by the object's time component twice, and the object's time component is enormous. It is essentially the entire magnitude of the arrow. One term survives. Exactly one, and it is the term that describes how the time direction changes as you move through space, which is to say, how the rate at which clocks tick changes from place to place. That is the mathematics telling you, in its own language, precisely what I have been telling you in pictures. For any object moving at any speed a human being will ever encounter, the entire content of the geodesic equation reduces to a single term, and that term is the gradient of the rate of time. Now run the arithmetic on that surviving term. Write down the geometry of the space around a spherical mass. Take the part that describes the rate of time. Take its spatial derivative, how it changes as you move up or down. Multiply by the appropriate factors and see what comes out the other side. What comes out is Newton's law of universal gravitation. Exactly, the inverse square dependence on distance, the proportionality to the mass, the whole thing. And here is the identity that falls out with it, which I think is the single most underappreciated sentence in the teaching of physics. Newton's gravitational potential, the quantity that generations of students have learned to calculate without anyone ever telling them what it physically is, turns out to be nothing other than the amount by which the local rate of time departs from its distant value. Read that twice, because it is the thesis of this entire video, expressed as an identity. Newtonian gravitational potential is the deviation of the rate of time. They are not related quantities. They are the same quantity, written down in 2 different centuries by people who did not know they were describing the same thing. When a physics teacher draws a hill and says that objects roll downhill toward lower potential, they are, without knowing it, drawing a map of the rate of time. The valley on that diagram is the region where clocks run slow. The height of the hill is the speed of the ticking, and rolling downhill is what an object does when it keeps moving forward, and the forward direction has a slope in it. So the boats and the oar were not a simplification. They were a translation. This also explains something that would otherwise be a strange coincidence, which is that you can calculate the satellite navigation correction using nothing but a Newtonian potential difference and a bit of arithmetic. You do not need tensor mathematics to get 38 microseconds a day. You do not need it because the potential difference and the rate of time difference are the same number in different clothing. The engineers who built that system were doing general relativity whether they thought of it that way or not. There is a lovely secondary consequence hiding in the same mathematics, and it is worth pulling out, because it reframes falling as something almost generous. Among all the possible paths an object could take between two events in spacetime, the one it actually takes, when nothing is pushing it, is the path along which it experiences the most elapsed time. Free fall is the aging maximizing route. Of every way a stone could get from your open hand to the floor, the way it actually goes is the one that lets it age the most. That sounds backwards at first, given everything I said in the last part about the falling object paying for its motion in the currency of time. Both are true, and the reconciliation is the interesting bit. Moving fast costs you elapsed time. Sitting far down in a gravitational well also costs you elapsed time. A falling object is threading between the two. It dips into the slow region, which costs, but it does so by moving, which also costs, and the trajectory it actually follows is the one where those two costs are balanced against each other to leave the largest possible total. Throw a ball, and its arc is not the cheapest path or the shortest one. It is the path that lets the ball live longest. Every object in the universe that is not being pushed is doing this, all the time, without any capacity to choose. Planets do it around stars. Stars do it around galactic centers. And a stone falling out of your hand is doing exactly the same calculation, using the same rule, at the same time. I said earlier that a slow clock is not a force. That is still true. It never becomes a force. What the equation shows is that it does not need to be one. A gradient in clock rates does the entire job that a force would have done, produces exactly the same numbers to as many decimal places as anyone has ever measured, and does it without anything ever pushing anything. There is a phrase of John Wheeler's that gets quoted constantly and understood about half as often as it gets repeated. Matter tells space-time how to curve, and space-time tells matter how to move. Almost every popular treatment of gravity explains the first clause at length. The bending, the warping, the dent in the fabric, and then it simply stops, as though the second clause were obvious. It is not obvious. The second clause is where the actual physics of falling lives, and everything I have just described is what it says. 3 things follow from this that are worth stating out loud. The first is that the word gravity does not name a force in this description. Look through the geodesic equation, and you will not find one. There is no force term. There is nothing corresponding to a push or a pull. There is a geometry, and there is an object moving through it as straight as it possibly can, and the straightest available path bends. The second is that free fall is unaccelerated motion. This sounds like nonsense until you internalize the rest. A falling object is not accelerating in the sense the equation cares about. It is doing the geometric equivalent of traveling in a straight line at constant speed. What we call its acceleration is a description relative to the ground, and the ground is the thing that is genuinely accelerating, being pushed upward off its natural path by the rigidity of the material underneath it. The third is a limit, and I am flagging it now, because the last third of tonight is about to walk straight into it. Everything in the argument I have just made depended on the object being slow. That is what killed all the other terms. That is what left the time curvature term standing alone. So what happens to something that is not slow? What happens to something moving at the fastest speed there is? We are going to get there, but first, there is an objection I have been putting off, and it is the one you would have raised 2 parts ago if you had been able to interrupt me. It is about objects that have no size at all. If you have been building the picture as I have described it, there is a hole in it, and I would like to put my own finger in the hole before somebody else does. The mechanism, as I told it, needs an object to have parts. 2 boats, a top and a bottom, something spanning a stretch of the gradient, so that different bits of it are in different rates of time. That is what produced the rotation. So what about a particle with no parts? As far as anybody has ever been able to measure, an electron is point-like. It has no measured radius. Experiments have pushed the upper bound on its size below 10 to the minus 18 meters, which is roughly 1,000th of the width of a proton, and there is no indication of internal structure at any scale probed so far. The same goes for the quarks inside protons and neutrons, and for the muon, and for the neutrino. In the standard model of particle physics, these things are treated as genuinely dimensionless points. A point cannot straddle a gradient. A point is entirely in one place, at one value of the rate of time. There is no top and no bottom. There is nothing to be mismatched. And yet electrons fall, not spectacularly. They are so light that electromagnetic forces swamp gravity by something like 40 orders of magnitude, so it is not easy to watch a single one drop. But there is no doubt whatsoever that they do. Every atom in your body contains them, and your body falls. So does every free electron in the solar wind. Gravity does not exempt point particles. There are 2 answers to this, and they are independent of each other, which is reassuring. The first is quantum mechanical. Nothing in the universe actually occupies a single, perfectly defined position. The uncertainty principle guarantees it. A particle with a precisely known position would have a completely undefined momentum, which is not a state anything is ever in. What particles have instead is a wave function, a distribution spread over a region of space, with an amplitude here and an amplitude there. An electron bound in an atom is smeared over a region about 1/10 of a nanometer across. A free electron in a coherent beam can be spread over a much larger distance than that. So even a genuinely point-like particle is never in one place, and therefore does sample a range of clock rates. That is a true answer, and it is satisfying, and I want to move past it quickly, because it is not the important one. If it were the only answer, it would mean that gravity somehow requires quantum mechanics in order to work, which would be a very strange claim about a theory Einstein completed a decade before quantum mechanics existed in its modern form. Here is the second answer, and this is the real one. General relativity does not need the object to have size, because the mathematics is not written in terms of differences across a finite gap. It is written in terms of derivatives. A derivative is not a comparison between 2 separated things. It is the rate of change of a quantity at a point, defined by considering an arbitrarily small separation and taking the limit as that separation shrinks to nothing. The gradient of the rate of time is a quantity that exists at every single point in space, on its own, whether or not there is anything there of any size to experience it. It is a property of the location. So the correct statement of the mechanism is not that the object's top and bottom disagree. It is that the object is moving through a region in which the time direction is continuously reorienting, and its own direction of travel therefore continuously reorients with it. That is what the geodesic equation says, and it says it pointwise. Size never enters. The boats and the oar are how you see it. They are a scaffold for the intuition, and I would give them to you again tomorrow. But the physics does not stand on them, and a good scaffold should be able to come down without the building falling over. It is worth separating this from a genuinely different effect that does need size, because the two get confused constantly. If an object is large enough that the gradient is measurably different at its top and its bottom, then it experiences a real stretching. Different parts of it are being rotated by different amounts. That is what produces ocean tides. That is what would eventually pull a person apart, falling into a small black hole. But that is a second-order effect, a difference of differences, and it is not what makes things fall. Falling is first order and needs no size at all. Tides are second order and need size. Keeping those two apart is most of the work of thinking clearly about this. Now, while we are in the business of correcting things, there are two claims that circulate around this material, and both of them are the same mistake made in opposite directions. The first is the claim, usually delivered with some triumph, that gravity is not real. You will find versions of this everywhere. Gravity is a myth. Gravity does not exist. There is no such force. And the popular finish, the Earth's surface must simply be accelerating upward at 9.8 meters per second squared. The first half of that is correct, and I have been arguing it for the last half hour. There is no force. An accelerometer in freefall reads 0. An accelerometer on your desk reads 9.8 upward. The desk is what is being accelerated, not the falling pen. The second half is where it goes wrong. The Earth's surface is accelerating in the technical sense of departing from a geodesic, of being held off the path it would otherwise take. That is a completely different statement from the surface physically moving upward through space at an ever-increasing speed. In flat geometry, those two things would be the same, which is why the confusion arises. In curved geometry, they come apart. Every point on this planet's surface can be permanently departing from its natural path without the planet getting any larger, in exactly the way that every point on the surface of a sphere can be curving without the sphere going anywhere. The second claim is the mirror image. Because gravity is really just the local rate of time, all you have to do to make something weightless is manipulate the local rate of time. Anti-gravity is therefore an engineering problem, not a physical impossibility. The trouble is that there is no known way to change the local rate of time except by changing the local distribution of energy and momentum, which is to say by moving mass around. The rate of time is not a dial with a separate input. It is set by what is there. Claims to the contrary have a long history and an unbroken record of failing replication. The most famous, involving rotating superconducting disks, reported in the 1990s to reduce the weight of objects placed above them, was never independently reproduced, despite serious attempts by well-equipped laboratories, including a funded replication effort at a national space agency that found no effect at all. General relativity does permit solutions with repulsive behavior. Every single one of them requires negative energy density in quantities and configurations that no observed form of matter provides, and in most cases, in quantities exceeding the total mass energy of large astronomical objects. So gravity is not a force, and that is not the same as gravity being fake, and neither statement gets you a hovering car. There is a third objection worth naming, because it is the most common and the most easily answered. It goes, if relativity is right, why do the engineers who run the satellite navigation system simply apply a fixed correction to the clocks, instead of measuring the effect fresh each time? Is that not just adjusting the data until it agrees with the theory? It is not. And the reason is that the correction was calculated before the satellites launched, published, and then found to be right. That is what a prediction is. If the predicted offset had been wrong by even a few percent, the positional errors would have shown up within days and been impossible to hide, because the system is checked continuously against ground stations at surveyed locations. The offset is not a fudge applied after the fact to rescue a theory. It is a number that was written down in advance and has been silently confirmed every day for nearly 50 years by several thousand million devices that would stop working if it were wrong. Which brings me to the picture that has probably done more to confuse people about this subject than every fringe claim combined. And it is not on the internet. It is in the textbooks. You know the image. A large sheet of rubber, stretched taut and held at the edges. A bowling ball placed in the middle, making a heavy dent. Then a marble rolled across the sheet, which curves toward the bowling ball and spirals in. That picture is in every textbook, every museum, every documentary, and a great many science classrooms as an actual physical apparatus, with an actual sheet and actual marbles. It is the single most widely reproduced explanation of gravity in existence. And I want to make the case that it is not merely simplified, but actively misleading, in 3 separate ways, each of which is worse than the last. The first problem is the one everybody notices eventually, usually around the age of 12, and then politely forgets. Why does the marble roll toward the dent? Because gravity is pulling it down into the dip. Real gravity, the Earth's gravity, acting on the marble, in the room where the demonstration is being performed. If you took that apparatus into orbit and set it up in the middle of a space station, nothing would happen at all. The bowling ball would not make a dent. The marble would not curve. The whole thing would simply drift. The most famous explanation of gravity in the world uses gravity to explain gravity. It is not an analogy. It is a loop. The second problem is deeper. Look at what the sheet is actually depicting. It is showing you a 2-dimensional surface, a slice of space, being deformed into a 3rd dimension. Space bending. That is the entire content of the image. But we established in the last part but one that for anything moving at ordinary speeds, the bending of space contributes essentially nothing to what you experience as gravity. The spatial curvature terms in the equation of motion are multiplied by the object's spatial velocity twice, and for anything slow, that number is so small that the terms disappear. So the rubber sheet is a picture of the part that does not matter. It shows you the negligible half in loving 3-dimensional detail, and the half that does the entire job, the variation in the rate of time, is not depicted at all, because a stretched sheet does not have a rate of time. There is nowhere on that apparatus to put it. Every person who has ever looked at a rubber sheet and thought, "I see, now I understand gravity," has understood the wrong component. And the third problem is the one that really costs you. The rubber sheet makes gravity look like a trap, a hole, a place where things get caught. It sets up an intuition in which space has holes in it and objects fall into them. And once that intuition is installed, it becomes almost impossible to think about a black hole correctly, or about orbits correctly, or about why this planet does not fall into the sun. So let me offer the replacement, built out of what we now have. There is no dent, there is no hole, there is nothing missing from space anywhere. What there is, around any concentration of mass or energy, is a region in which the rate of time varies smoothly with position, running fastest far away, slowing as you come inward, with no boundary and no edge. And through that region, everything is moving, not into a hole, forward through time, at full speed, continuously, without the option of stopping. The right image is not a ball in a dip. The right image is a wide, slow, invisible current, running in a direction you cannot point at, in which every object in the universe is being carried at the same enormous speed, and which does not run quite evenly. It runs a little slower where the mass is, and anything crossing a region where it runs unevenly gets turned. If you want a physical analogy that actually works, use light entering glass rather than balls on rubber. When light passes from air into water at an angle, it bends. Nothing pulls it. What happens is that the propagation speed differs slightly on one side of the beam from the other, and that difference in rate across the width of the beam turns it. Refraction is not a force, it is a gradient in the rate of propagation, doing to a light beam precisely what a gradient in the rate of time does to a falling stone. And the mathematics of the two cases is not merely similar. You can compute the bending of starlight around the sun exactly by treating the region around the sun as a medium whose refractive index varies with distance, and the answer comes out correct. That is not a coincidence, and it is not a teaching trick. It is the same geometry described in optical language. There is another framing that some physicists prefer, and it is worth having in your pocket, because it makes certain problems trivially easy. In it, you treat space itself as flowing inward toward the mass, and objects as being carried along by the flow, like leaves on a river. It is not a competing theory. It is a particular choice of coordinates, and for a non-rotating black hole, it turns out to be exactly right rather than approximately right. What is nice about it is what it does to the idea of an escape velocity. In that picture, the horizon of a black hole is simply the surface where the inward flow of space reaches the speed of light, so that a photon swimming outward at full speed against the current makes no progress at all, like a fish swimming upstream in water moving exactly as fast as it can swim. That river picture and the time gradient picture are not rivals. They are two ways of holding the same geometry, and each of them makes different things easy to see. What they agree on absolutely is the thing the rubber sheet gets wrong. Nothing is being pulled. There is a whole small field built on taking that river seriously, incidentally. If a horizon is just the surface, where a flow outruns the waves traveling through it, then you should be able to build one out of anything that flows. And people have. Physicists have made analog horizons in flowing water, in ultra-cold gases, and in light traveling through optical fibers, and have gone looking for the faint radiation that a real horizon is supposed to emit. Whether those experiments truly reproduce the astrophysical case is still argued over. But the fact that the analogy is close enough to build hardware around tells you something about how little of this is really about mass, and how much of it is about rates. That is the picture I would put in the textbooks. Not a dent in a trampoline, a gradient in a rate, the same thing that turns a light beam entering water, the same thing that swings a pair of joined boats toward the bank, the same thing that is pinning you to your bed tonight. And it has a consequence the rubber sheet actively hides. On the rubber sheet, an object in a dent is trapped, and it takes energy to climb out. In the real picture, nothing is trapped by geometry. Things simply follow the straightest path available, and if that path takes them around and back out again, out they go. This is why an orbit is not a balance between falling and moving fast enough not to fall. That is a description you have certainly been given, and it is not really true. An orbit is just a path. The moon is not fighting anything. It is going as straight as it is possible to go in a region where the time direction slopes, and the straightest available path happens to close on itself. It has not escaped anything, and it is not resisting anything. It is falling, continuously, forever, along a line that comes back. There is one more thing that only becomes visible once you drop the trampoline. If gravity is a slope in the rate of time, then a region where the slope becomes infinitely steep is not a place where the pull becomes infinitely strong. It is a place where the rate of time, relative to the outside, falls to zero. That is what the horizon of a black hole is, and it explains something the dent picture makes incomprehensible. Why nothing, not even light, comes back out. It is not that the pull is too strong to escape. It is that beyond that surface, the direction we call inward stops being a direction in space and starts being a direction in time. Falling further in becomes as unavoidable as tomorrow, and for the same reason. But I have been putting something off for 3 parts now, and it is time to face it. Because everything I have built rests on one assumption, and there is an entire category of thing in this universe for which that assumption is flatly, completely false. Everything I have told you tonight depends on one thing being true, that the falling object has motion through time available to convert. That is the engine. The object is traveling forward through time at the maximum rate. The time direction slopes. The object's direction of travel rotates, and a sliver of its temporal motion becomes spatial motion. The whole mechanism is a trade, and a trade requires the trader to be holding something. Now consider light. A photon travels through space at the speed of light. That is not a coincidence of naming. It is a definition of the thing. And if you take seriously the reading I introduced in part 1, that everything moves through space-time at a fixed rate divided between time and space, then a photon has spent absolutely all of it on space. There is nothing left over, which means a photon does not move through time at all. I want to be precise here, because this is one of the places where popular explanations get sloppy in a way that actually matters. A photon does not have a slow clock. It does not have a nearly stopped clock. Along its own path through space-time, the interval, the quantity that corresponds to elapsed time for anything else, is exactly 0, not approximately 0. 0 identically, as a matter of the geometry, rather than as a limit that something approaches. The technical statement is that a photon does not have a 4 velocity. That arrow of fixed length I have been talking about all night is defined as the rate of change of position with respect to the object's own elapsed time. And if the object's own elapsed time is always 0, that definition divides by nothing. It does not produce a small number. It produces no number at all. Light is described instead by a related quantity, a 4 momentum, which is a peculiar object with non-zero components and 0 total length, a thing that points and has no length. So a photon, by the mechanism I have spent this entire video building, should be completely immune to gravity. It has no temporal motion to rotate. It has nothing in the time column of the ledger. There is nothing for the gradient to take a sliver of. Whatever a slope in the rate of time does to an ordinary object, it should do nothing whatsoever to light. And light bends. It bends constantly. It bends so reliably that we have built an entire branch of astronomy on it. Look at almost any long-exposure image from a large telescope, and you will find galaxies smeared into long, thin arcs, curved around invisible concentrations of mass, sometimes wrapped into complete circles where the alignment happens to be near perfect, and the light from a single distant object arrives from every direction around the intervening mass at once. Quasars appear as 2, 4, sometimes 6 separate images of the same object, because the light took several different routes around a galaxy on its way here, and each route bent by a different amount. Astronomers do not treat this as a curiosity. They use it as a measuring instrument. Gravitational lensing is how we weigh clusters of galaxies. It is how we map the distribution of dark matter by measuring the distortion of the shapes of background galaxies across huge areas of sky and reconstructing the mass that must be there to produce it. It is how one particular pair of colliding clusters showed us 2 objects that had passed through each other with their visible gas left behind in the middle and their gravitational mass carried on ahead, which is one of the strongest pieces of evidence that dark matter is a substance rather than a modification of the law of gravity. That colliding cluster observation is worth a moment on its own, because of how cleanly it separates 2 things that normally travel together. When 2 galaxy clusters pass through each other, the galaxies themselves mostly miss, because stars are tiny compared with the distances between them. The hot gas does not miss. Gas collides with gas, slows down, heats up, and gets left behind in the middle, glowing in X-rays. So if the visible gas is where most of the mass is, the lensing should be strongest in the middle. It is not. The lensing follows the galaxies, out ahead on either side, where almost none of the visible matter ended up. Something with mass and almost no interaction went straight through the collision without noticing it. And the only reason anyone can say so is that light bent around it on the way here. Every single one of those observations is light being turned by mass. And there are smaller scale versions that are even harder to argue with. When a foreground star passes precisely in front of a background one, the background star briefly brightens as its light is focused around the intervening mass. That effect has been used to detect planets in orbit around stars thousands of light years away. Objects nobody has ever seen and never will. The technique works because the bending is exactly as predicted, every time, to the precision of the photometry. Light bends. There is no possible way around it, and no serious person has tried to find one for 100 years. There is a closely related effect that is, if anything, even more pointed for our purposes. When a radio signal passes close to a massive body on its way somewhere, it does not merely bend. It arrives late. This is called the Shapiro delay, after the physicist who predicted it in 1964, and it was confirmed within a few years by bouncing radar off Mercury and Venus when they were on the far side of the Sun. It has been measured far more precisely since. In 2003, radio signals sent to and from a spacecraft passing behind the Sun were delayed by an amount matching the general relativistic prediction to within about 2 parts in 100,000. Think about what a delay means. The signal did not slow down in any local sense. Light always travels at the speed of light where it is. What happened is that it spent part of its journey in a region where the rate of time is slower, and so, measured from out here, the crossing took longer. That is the time gradient acting directly on light, and it is not in dispute, which makes the problem sharper rather than softer. The gradient clearly does something to photons. It just should not be able to turn them. And there is one further wrinkle that makes the naive picture even more uncomfortable. The bending of light is not a small correction sitting on top of something else. Near a sufficiently compact object, it becomes total. At a distance of 1.5 times the horizon radius of a black hole, there is a surface called the photon sphere, where light bends so completely that it can travel in a circle. A beam fired horizontally there would go all the way around and hit you in the back of the head. If you could somehow stand on that surface facing sideways, you would be looking at yourself. That is not something you can produce by taking the mechanism I have described and applying it to an object with nothing in the time column. So I appear to have a problem. I have spent the better part of an hour telling you that gravity is the conversion of temporal motion into spatial motion, and I have just been handed a category of object that has no temporal motion and is affected by gravity anyway. There are 3 ways this could go, and I want to name all 3 before I tell you which one is true, because 2 of them are the ones you would reasonably expect. The first. The mechanism I described is simply wrong, and the fact that it reproduces Newton's law exactly for slow objects is some sort of coincidence, or an approximation that happens to work in one regime and fails outside it. That would be an unpleasant outcome, and it would mean this video has been an elaborate lie with a good ending. The second, the mechanism is right, and there is some additional, separate effect that handles light, a special case, bolted onto the side, that deals with the massless particles. The third, the mechanism is right and incomplete, and the way in which it is incomplete is precisely measurable, so precisely that the measurement was made in 1919, by hand, on photographic plates, on an island off the coast of West Africa, and the number that came back tells you exactly what fraction of gravity is the warping of time. It is the third one. And notice, before we go there, that the third option is the only one of the 3 that would count as evidence. The first would be a refutation, the second would be an excuse. Only the third makes a number. A specific, checkable number that could have come out wrong and did not. I want to be honest about how much I like this, because it is not often that a story does this. The objection I have just raised is not a hole that gets patched. It is not something the theory survives despite. The resolution of it is the single most direct measurement anyone has ever made of the claim at the center of this video, and it was made 4 years after Einstein wrote the theory down, and it made him internationally famous overnight. And the number involved is 2. Everything depends on a factor of 2. In 1911, 4 years before he finished general relativity, Einstein published a calculation. He had the equivalence principle. He had the argument from the accelerating box. He had worked out, as we did in part 3, that clocks must run at different rates, at different heights, in a gravitational field. And he realized that this alone should be enough to bend light. Because if the rate of time varies from place to place, then a wavefront of light crossing that region has one edge in slightly slower time than the other, and a wavefront whose 2 edges advance at slightly different rates turns. It is the same refraction argument I gave you 2 parts ago, applied to the sun instead of a pane of glass. So he ran the numbers for starlight grazing the edge of the sun, and he got a deflection of about 0.83 seconds of arc. To give you a sense of that angle, 1 second of arc is 1/3600th of a degree. 0.83 seconds of arc is roughly the angle subtended by a small coin seen from about 4 kilometers away. It is small, but it is not impossibly small. In 1911, it was right at the edge of what careful astronomical photography could detect, and Einstein knew it. He wrote in that paper that it would be desirable for astronomers to test it, and he specifically noted that the measurement would have to be made during a total solar eclipse, since otherwise the sun's own light would drown out any star near enough to its limb to matter. Several expeditions tried in the years that followed, and every one of them failed, for a different reason each time. A German team, led by Erwin Freundlich, travelled to Crimea to observe the eclipse of August 1914, and was arrested as enemy aliens when the First World War broke out days before totality. Their equipment was confiscated. It was, as it turned out, an extraordinary piece of luck for Einstein, because his 1911 number was wrong. In November 1915, Einstein completed general relativity, and when he redid the light-bending calculation with the full theory, the answer came out at 1.75 seconds of arc, exactly twice the old value. That doubling is not a rounding error, or a refinement, or a correction to a coefficient. It is a whole extra half of the effect appearing from somewhere, and where it came from is the entire point of tonight. The 1911 calculation used only the time part, only the variation in the rate at which clocks tick from place to place. That is all Einstein had in 1911, and it is exactly the mechanism I have spent this video building. It gave him 0.83 seconds of arc. The 1915 theory included the other component too, the curvature of space itself, the part the rubber sheet actually depicts, the part that contributes essentially nothing to a falling stone. And for light, that part contributes precisely as much as the time part does. Not a little, not most of it, the same amount. So the answer doubled. Now go back to part 8 and look at why. The geometric quantities in the equation of motion get multiplied by the object's direction of travel through spacetime twice. For a slow object, the spatial component of that direction is essentially 0, so the space curvature terms disappear, and only the time term survives. Which is why, for everything slow, the gradient of time is the whole of gravity. But light is not slow. Light is the fastest thing there is. Its direction of travel through spacetime is as far from the time axis as it is possible to get, and its spatial component is not small, it is maximal. So the space curvature terms are not suppressed at all. They contribute at full strength, exactly matching the time terms. Which means that factor of 2 is not a curiosity of history, it is a measurement. It is the universe answering, with a number, the question this entire video has been circling. How much of gravity is the warping of time? For anything slow, all of it. For light, exactly half. And that answer was confirmed not by an argument, but by 2 ships. The 29th of May, 1919. A total solar eclipse, with the darkened sun positioned in front of the Hyades, an unusually rich cluster of bright stars, which meant an unusually good chance of catching several close to the solar limb. The Astronomer Royal, Frank Watson Dyson, had spotted the opportunity years earlier and organized 2 expeditions to opposite sides of the Atlantic to hedge against weather. One went to Sobral, in northern Brazil. The other, led by Arthur Eddington, went to the island of Principe, in the Gulf of Guinea, off the coast of West Africa. On Principe, it rains all morning. Eddington has one chance. An eclipse lasts a few minutes and does not come back. There is no second attempt, no rescheduling, no waiting for a better day. He has crossed an ocean and carried delicate glass plates through a tropical summer for an event that will be over before he can properly think about it. The cloud does not break until shortly before totality. He gets 16 plates. Most of them show nothing usable. 2 show stars. He develops them on the island over the following days, in the heat and the humidity, and compares the star positions on those plates against comparison plates of the same field taken months earlier in Oxford, when the sun was somewhere else in the sky entirely. He is looking for a displacement of well under 2 seconds of arc, measured with a micrometer, by hand, on an equatorial island, on glass that has been carried halfway around the world and back. The Principe plates gave 1.61 seconds of arc, plus or minus 0.3. The Sobral 4-inch lens gave 1.98, plus or minus 0.12. The Newtonian prediction: if you treat light as a stream of ordinary particles falling in a gravitational field, which is the closest thing to a rival answer that existed, was about 0.87 seconds of arc. Almost exactly Einstein's discarded 1911 figure, and for a related reason. It too accounts for only half the geometry. Einstein's number was 1.75. The results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London on the 6th of November 1919. The following morning, Einstein, who had been essentially unknown outside physics, was on the front pages of newspapers around the world. The Times of London ran a headline about a revolution in science and a new theory of the universe. Within weeks, he was the most famous scientist alive, and he stayed that way for the rest of his life, on the strength of a number measured on a photographic plate on an island. I should be honest about the quality of that data, because the story is often told as though it were decisive on the day, and it was not. There was a third set of plates from Sobral, taken with a different instrument, which gave a result close to the Newtonian value. Eddington and Dyson discounted them on the grounds of a suspected focus problem caused by the sun heating the telescope's mirror, and there has been a long historical argument about whether that exclusion was justified. Modern reanalyses of the surviving plates generally support the exclusion on technical grounds, and a remeasurement with modern equipment in the 1970s gave a value in good agreement with Einstein. But the honest summary is that the 1919 result was suggestive rather than conclusive. The eclipse measurements continued for decades and did not converge quickly. Expeditions through the 1920s, 30s, and 50s produced values scattered from around 1.2 seconds of arc up to around 2.7, with error bars large enough that partisans of either answer could find something to like. Eclipse photography is simply a very difficult way to measure a very small angle. You have a few minutes of totality. You cannot control the weather. The instrument is sitting outdoors in changing temperature, and you are comparing plates exposed months apart in different climates. The remarkable thing is not that the results were noisy, it is that the mean of all of them sat closer to Einstein's number than to Newton's, decade after decade, using instruments that were never really up to the job. What settled it was not optical astronomy at all. It was radio. From the 1970s onward, very long baseline interferometry made it possible to measure the deflection of radio waves from distant quasars passing near the Sun, without needing an eclipse and without photographic plates. Those measurements confirm the general relativistic value, the doubled one, to a precision of around 1 part in 10,000. The spacecraft measurement in 2003 pinned the closely related quantity to about 2 parts in 100,000. There is a number in modern gravitational physics that exists specifically to track this. It is a parameter that measures how much spatial curvature a given amount of mass produces, relative to what general relativity predicts. If the time gradient were the entire story, and space were not curved at all, that parameter would be 0. If space curved twice as much as Einstein said, it would be 2. General relativity requires it to be exactly 1. Measurement puts it at 1, to within about 2 parts in 100,000. That parameter is the precise experimental statement of the boundary of everything I have told you tonight. The time gradient is not most of gravity, or an approximation to gravity. For anything moving slowly, it is all of gravity, and the number confirms it. For light, it is exactly half, and the number confirms that too, to 5 decimal places. The objection did not break the mechanism. The objection measured it. So let me say the thing plainly now, because it has been earned. Gravity is not a force acting on you. It is what your own unavoidable motion forward through time looks like in a place where the rate of that motion is not the same everywhere. You are not being pulled down, you are being held up. Every part of that sentence is now paid for. You are moving through time at the maximum rate anything moves through anything, and you have never once had the option to stop. The rate at which time passes is not uniform around a mass. It slopes, continuously, smoothly, all the way down to the smallest scale anyone has managed to measure, which is currently about 1 millimeter of cold strontium in a laboratory in Colorado, and which shows no sign of having a bottom. Anything moving through a sloped region has its direction of travel rotated toward the slow side, in the way 2 boats joined by an oar swing toward the bank. That rotation is falling, and it is paid for out of your motion through time, at an exchange rate set by the speed of light, which is why an unmeasurable change in the ticking of a clock buys an acceleration that can kill you. And for anything moving at ordinary speed, that gradient of time is not a contributing factor. It is the entire mechanism, confirmed by the fact that light, which has nothing in the time column, bends by exactly twice as much. So when you feel your weight tonight, what you are feeling is not gravity. You have never felt gravity. In free fall, the one condition in which gravity is unambiguously the only thing acting, you feel nothing at all, and an accelerometer strapped to your chest reads 0. What you are feeling is the mattress, the floor beneath it, the joists, the foundations, the crust of a planet. Something solid, pushing upward against you, continuously, for every second you have been alive, in order to keep you off the path you would otherwise take. The floor is the only thing accelerating in this room. And that means the sensation you have spent your whole life calling weight is not the sensation of being pulled toward the earth. It is the sensation of being prevented, of being interrupted, permanently, in a motion you never chose and never noticed. There is a version of you that was never interrupted. That went where the geometry was taking it, and the only reason that version does not exist is a few centimeters of material that happens to be rigid. Take the material away, and nothing pulls you, nothing acts on you. You simply continue. And continuing, here, means going down. There is one more thing I owe you, and it is the honest boundary of everything I have said tonight. I have explained how a gradient in the rate of time produces gravity. I have not explained why mass produces a gradient in the rate of time. Nobody has. Einstein's field equations state the relationship. They say that the distribution of energy and momentum determines the curvature of spacetime, and they say exactly how much, and every prediction that has ever been extracted from them has been correct. 38 microseconds a day in a satellite constellation. 43 seconds of arc per century in the precession of Mercury's orbit. The 1.75-second deflection at the edge of the Sun. The steady decay of a binary pulsar's orbit, matching the energy carried away as gravitational waves to better than 2 parts in 1,000. Over 50 years of watching. The ringing of 2 black holes merging 1,000 million light-years away, arriving here as a change in the length of a 4-kilometer laser arm, smaller than the width of a proton. It is arguably the most successful physical theory ever written, and it does not say why. It states the relationship as a fact about the world, in exactly the way Newton stated the inverse square law as a fact about the world, and left the mechanism to somebody else. There is a machine here. We can read every gear on it. Nobody has found the place where the power comes in. The attempts to go underneath are real and serious, and none of them has produced a confirmed experimental signature. In 1995, a physicist named Ted Jacobson showed that Einstein's field equations can be derived from thermodynamics. That if you assume entropy is proportional to horizon area and apply the ordinary relationship between heat and entropy, the equations of general relativity fall out as an equation of state, the way the gas laws fall out of the statistics of molecules. If that derivation is telling us something true, then spacetime curvature is a bulk statistical property of something underneath, and asking why mass warps time would be like asking why a gas has a temperature. A real question, asked at the wrong level of description. I should also be straight with you about the word cause, because I have been leaning on it hard all night, and it is the one part of tonight that is a reading rather than a result. There are 3 positions a careful physicist can hold about all of this, and they agree on every measurement that has ever been made. The first is the one I have argued. The gradient of time is the mechanism, and gravity is what that gradient does to things that are moving. The second says that the curvature of spacetime is the primitive object, that the time gradient is simply one of its components, and that singling out that component as the cause is a choice of emphasis that our own slowness makes convenient. The third says that both of them are surface descriptions of something else entirely. That spacetime and its geometry emerge from a deeper structure of information or entanglement, and that asking whether time causes gravity is like asking whether the pressure of a gas causes its temperature. Nothing currently distinguishes these 3. No experiment anyone has performed, and no experiment anyone currently knows how to design, comes down on one side. What decides between them is which object you take to be fundamental, and that is not a question measurement has so far been able to reach. What I would say in defense of the first reading is simply this: it is where the number comes from. In the regime we actually live in, if you want to calculate how fast something falls, the quantity you differentiate is the rate of time, and every other component of the geometry contributes essentially nothing. That is not a philosophical preference. That is where the 9.8 comes from. And there is a place where the whole picture becomes genuinely unstable, and it is not far away. Take a small mass and put it into a quantum superposition, here and also over there, in the way that single atoms and increasingly large molecules routinely are in laboratories. The rate of time nearby is determined by where the mass is, so the rate of time is now in superposition. A clock sitting next to that mass is in a superposition of ticking at two different rates, which raises a question that nobody currently knows how to answer. In what sense is there a rate of time at all? Proposals exist to test this. Two groups, working independently in 2017, described experiments that would look for whether gravity can entangle two masses. A positive result would be strong evidence that the gravitational field is itself quantum, rather than a classical backdrop that quantum things happen in front of. The masses required are around 100 million millionth of a kilogram, held in coherent superposition for something like a second, which is at, and possibly just past, the edge of what levitated optomechanics laboratories can currently do. People are building these. The answer may arrive within the working lifetime of anyone listening. Until then, we are in the strange position of being able to say, with total precision, how the most familiar force in human experience operates, and not being able to say what it is. So here is where I would leave you tonight. Somewhere between the crown of your head and the soles of your feet. The rate at which time passes changes by about 1 part in 10,000 million for every meter of separation. It has been that way since the day you were born. Over the whole of your life, your feet will fall behind your head by around 470 nanoseconds, and there is nothing you can do about it, and nothing that would be different if you could. That difference is not a curiosity. That difference is the reason you have weight. It is the reason your heart has to work harder to push blood upward than downward. It is the reason trees have a maximum height, and land animals have a maximum size, and the oceans stay where they are. Everything that has ever fallen, on this planet or any other, fell because of a slope like that one. You are lying in it right now. It runs through you, from your head to your feet, without gaps, without a boundary anywhere. And the only reason you are not moving along it is that something underneath you is pushing back. Thank you for spending this time with me, walking slowly through the strangest and most ordinary thing in physics. If you found this worth staying awake for, or worth falling asleep to, a like or a subscribe would mean a great deal. It genuinely helps me keep making these. And remember, the next time you set something down on a table and it stays there, nothing is holding it up except the table, and nothing was ever pulling it down. Good night, and may you never feel your own weight quite the same way again.